Hi, my name is Matthias Herbener. I'm in Math 2000 here at Challenge 2016, and this is going to be my third video for calculus. So in this video, we're going to talk about how to find, or how to, prove the area of an ellipse, which is, an ellipse is a shape kind of like a circle, but more elongated. In simpler terms, it's, I guess you could call it an oval, but it's like that. And so the equation of a circle, right, is x squared plus y squared equals r squared. In contrast, the equation of an ellipse is x over a quantity squared plus y over b quantity squared equals 1. So, and a is going to be this distance right here. A is going to be this distance right here along the x-axis, and b is going to be this distance right here. And so those are the two radii of the ellipse in this case. Like a corresponds to x and b corresponds to y. And so if you go on, if you look it up on Google, just search area of an ellipse, the formula that you'll get is going to be pi AB. Which, if you compare it to a circle, makes sense, because the area of a circle is pi r squared, and it's the same, except in this case, r and r are a and b, and since they're not equal to each other, it's just pi ab. But let's prove this using calculus. So an ellipse is symmetric along both of its axes. So in this case, since this one is centered at the origin, it's going to be symmetric along the x-axis and the y-axis. So using that, we can say that this one part in the first quadrant, right, is the same as each of the other four parts, and thus you can find the integral that you can set up is 4 times the integral that represents the area of this one function right here. And so since this distance is a and it goes from origin out, this point right here is going to be a0, right? X, or a units down the x-axis. So what you're going to get is you're going to get 4 times the integral of from 0 to a of whatever this is when you solve for y.
Stop.
Did it run out of space?
No, you're good. You're good. Continue.
Okay. So if you solve this for y, you just subtract x over a squared from both sides, and take the square root and multiply by b, and what you'll get is that y equals a positive negative b times the square root of 1 minus x over a quantity squared. In this case, we don't need to worry about positive or negative because it's all going to be above the x-axis, so it's all positive. So what we're going to get is the integral of b times the square root of 1 minus x over a squared dx. And so since b here is going to be a constant, we can pull that out, so we get 4b times the integral from 0 to a, and we're going to leave this blank for now. So what we need to do in order to be able to solve this is use the trig substitutions. And to do that, we need a triangle, right? A right triangle, to be exact, with there's theta and there's a right angle. And so then coming back to here, if you if you multiply both of the terms inside the radical by a squared, then that will come out to be a squared minus x squared. And you can use that more easily in a trigonometric sense. But to balance that out, since you multiply it by a squared under the radical, you have to divide by a outside the radical. And since a is a constant, you can bring that out here. So you're going to get 4b over a times all that dx. And so you come back over here, and a squared minus x squared, if you think back to the Pythagorean theorem, the square root of that is going to be one of the legs. Because if a is the hypotenuse and x is the other leg, then this leg is going to be a squared minus x squared just because of the Pythagorean theorem. Because if you square this and you add x squared, then you're going to get a squared. And so what you can do with this is you can now take sine of theta is equal to x over a, opposite over hypotenuse, and then you can move that around to get x is equal to a sine theta. Right, and so you can plug that in here. So going on, 4b over a is equal to the integral, no bounds just yet, because we need to convert those, of a squared minus x squared, so we're going to have a squared sine squared theta, and then we need to convert the dx as well, so we just have to take the derivative of both of these sides, so dx is going to be a cosine theta d theta, and so then we're just going to plug that in over here, a cosine theta d theta, and you'll notice there's an a here and a 1 over a here, so we can just, that can cancel out, so we can just get rid of that. And so now you can also factor out an a squared from here, so that would be the radical, or the square root of a squared times the quantity 1 minus sine squared theta. And since this is because of square roots, radical properties, we can factor out the square root of a squared, so we'll be left with a times the square root of 1 minus sine squared theta. And since a is a constant, we can bring it out here to get 4ab as the, I guess, coefficient of the integral. And then this is going to go from a squared minus a squared sine squared theta to 1 minus sine squared theta. And we can use our trig identities to solve that one as well, because as we know, sine squared of theta plus cosine squared of theta is equal to 1. So 1 minus sine squared of theta is equal to cosine squared. So we can plug that in here, and so we get 4ab times, before I go back to that step, we'll write this in here. Right, so the bounds. Since we converted it to terms of theta instead of terms of x, we need to convert the bounds from terms of x into terms of theta. And so to do that, we just have to use this relationship right here, x equals a sine theta. So we plug in both of these values as x and solve from there. So we're going to get, the upper bound is going to be a equals a sine theta, so 1 equals sine theta, and then theta is going to be the inverse sine of 1, which is just pi over 2. And then for the bottom bound, you get 0 equals a sine theta. Divide both sides by a, you get 0 equals sine theta. Theta is the inverse sine of 0, which is also 0. So these bounds are going to be 0 to pi over 2. And same down here. Alright, and so now we have this. And obviously we have cosine, the square root of cosine squared theta, that's just going to cancel out to cosine of theta times cosine of theta. So our next step is going to be 4ab times the integral from 0 to pi over 2 of cosine squared theta d theta. And now normally this wouldn't be very nice to look at when you're having to solve it, but we can use our, I guess, square to double angle identities to make this easier. And as we know, cosine squared theta is equal to 1 plus cosine of 2 theta over 2. So we can plug that in here. We can take out the, I guess, 1/2, because this is the same as 1/2. 1 plus cosine 2 theta, right? We can factor out the 1/2 and, or not factor, but we can pull out the 1/2 and put it in front, so that our next step would be 2ab, 4 times 1/2, of the integral from 0 to pi over 2 of 1 plus cosine 2 theta, d theta, and that is a lot easier to integrate. So we're going to get 2ab, and then the antiderivative is going to be theta plus 1/2 sine 2 theta, right? 1/2 to cancel, or to balance out with the chain rule. So then we're going to evaluate that from 0 to pi over 2 So we're going to have 2ab times, okay, so pi, or theta is going to be pi over 2 plus 1/2 sine of pi, because 2 pi over 2, and that, and then minus theta times 0 to 0, plus 1/2 sine of 0. Alright, sine of pi is 0, so that's gone. 0, 0, sine of 0 is 0, so that's gone. And so what we're left is 2ab times pi over 2, or pi ab. And that is the answer that you're looking for. Alright, again, I'm Matthias Servener, I'm in Math 2000, and this has been video 3.